Okay, so we talked about in previous classes the basic quantities that we use in fluid mechanics. They are basically the velocity field and the pressure field. And we are going to talk about pressure today. And to simplify, we are just talking about pressure when there is no motion. If there is no motion, there are no shear stresses in the fluid, and you have essentially a stagnant pool of fluid, and we would like to know for this simplifying case what the pressure field is. So there are lots of situations where you'd like to know the pressure variation on bodies that are immersed in the fluid. So think the supporting platforms of oil rigs or undersea pipelines or cables that transfer data. There are lots of situations where there's no flow, but because of the shape of the object, there's a pressure variation along the object surface, and as a result, the net force and moment on the body is something that has to be calculated. It's not very straightforward. So one would like to know what the pressure field is in a stagnant liquid. And so let's say a simple case we have, first let's talk about pressure at a point before we go ahead and try to look at pressure variation and force variation. So let's say I've got some fluid and I have my surface, and I'm going to take an elemental surface, very small in area, let's say some particular orientation with respect to gravity, and I'd like to know what the force or equivalently the pressure on this elemental area is on this surface. First question that I'd like to know is, the answer to is, well, what if I had this angled this way versus angled this way versus angled this way? Is there a functionality? Is there an angle dependence? How does the pressure vary with respect to angle of orientation of the surface? And how does it vary with respect to the depth and the XY location, and so on. So let's just tackle the angle dependence first. So let's say I have some imaginary coordinate system. I've got one of these elemental areas occupying some kind of volume where the coordinate system can be drawn like this. And let's say that's X, that's Y, and that's Z. Actually, let's make that X, just so that we have a right-angled system, X right-handed coordinate system. So that's X, Y, Z that way. And there's an angle that this surface is making with respect to the XY plane, and gravity, of course, is acting at the center of gravity, center of mass in this case, and acting downwards along Z. So we'll do the first of our free body diagram analysis that we'll do throughout the course. Ultimately, this course is a course in mechanics. We are going to do F equals ma a million times. In this case, we are going to do F equals ma for a stationary object. So let's say this height is delta Z, that length is delta Y, and this is delta X. So there's a force acting on the vertical faces, on the faces which are aligned to the XY plane, and then there's this normal force acting on the inclined surface. So let's call that PS. Let's call the force on the vertical face P. Let's see, this has a normal with respect to y, so let me call this Py, and that has a normal with respect to, that's a normal to the z direction, and so let me call that Pz. Now, if I were to balance things in the horizontal direction, I would have Py times this surface area, which is delta x delta z. That horizontal force would be balanced by the horizontal component of P sub s. So let me write that down. So I have summation of forces in the y direction is equal to Py times the area, so that's delta x delta z, minus the horizontal component of the pressure force, that's Ps times delta x delta s sine theta, where delta s is the area, the hypotenuse, so this would be delta s. And this should be equal to ma, and for now we'll just say set that to 0. In principle, this whole fluid element could be accelerating. And if I were to write a similar equation for the vertical direction, I would say P sub s, P sub z, that's the bottom face, P sub z delta x delta y minus P sub s delta x delta s cosine theta, that in this case needs to be equal to the weight of the fluid element. So that would be gamma delta s delta y delta z by 2. This being the delta V, the volume. So if I were to simplify this, I would make use of the fact that delta y is delta s cosine theta, delta x is related to, delta z is related to delta s through the sine of the angle. So plug these in back into your x and y, into your y and z momentum equations, and what you get is P sub s is P y and P sub s is also equal to P sub z. So essentially we get something, a relation in which the angle dependence seems to have disappeared. So in other words, pressure at a point is independent of surface orientation.